My name is Tim Hanke. I studied at the university, at the Technical University in Hamburg. I made my master degrees in energy systems, and since 2023 I'm at XRG and I'm developing the SMArtInt Plus library, and I'm the library officer for this library and also for the smaller version or the open source version, the SMArtInt library. For those of you who never heard of SMArtInt or SMArtInt Plus, maybe I will start with the core of SMArtInt and SMArtInt Plus. So SMArtInt, and SMArtInt stands for Simple Modelica Artificial Intelligence Interface, and we can use this interface to integrate neural networks into Modelica tools. And so in this case, it's Daimler and Open Modelica. For SMArtInt right now, it's also possible to use in Model on Impact. For SMArtInt Plus, there's still some issues, but we're working on that, and that should also be in the future possible. And right now, there are two formats or two model types that we can implement. One is TensorFlow Lite, and the other one is ONNX. I will come to that later and tell a little bit more details. And what we can use this for is that we can use it to exchange or substitute some functions or models that have easy input-output behavior, but we are also able to replace more dynamic components and submodels. And as you can see, SMArtInt was developed or partly developed within a research project that was called SPROGI. And so here's the main feature of SMArtInt and also then the core of SMArtInt Plus. This is the working principle. We have our Modelica simulation where we get then some inputs for our neural network. These are then provided to an external C function. And in this external C function, we have the inference of the neural network. And then the outputs, the predictions of the neural network are then going to be brought back to the simulation, and we can then use them there. As I already said earlier, we are supporting ONNX. ONNX stands for Open Neural Network Exchange. So it's an exchange format that allows to include multiple frameworks for training neural networks. Like I think the most famous ones are PyTorch and also TensorFlow. So there you see there's some overview of the most popular, I think, that are supported. So there are a wide range of possible frameworks to use. With that we come to SMArtInt Plus. So SMArtInt Plus is the commercial version of the SMArtInt library, and it extends the functions. So we have in the middle our core SMArtInt, and we extend it with advanced interfaces. I think all of these points we see here we will use in this tutorial. We have an additional data generator that helps us to generate some training data, as well as a network generator to train neural networks. And we have a model generator to bring our trained models easily back into Modelica. And we have one of our features, the extrapolation warning, that can be used to see if our network is getting inputs that it's not trained on, because then the prediction quality can be bad sometimes. So we will also take a look at this, and we will see how it works and what it can be used for. So I don't know if you already opened the SMArtInt Plus library, if you have it installed already. It's a very simple basic structure. So there are some information where you also have some documentation on how things work, but there's also documentation in the main models or the main functions of the library. We then have different testers where we have some examples for the functions and how to use the library and how it works. Some base classes that we use or were used inside of the library. And in this blocks part, they are the main functions, and they can find all these things I showed before. And the internal package is more or less for internal functions and the external C code. So that's probably not for the user, but yeah. As we see before, this is this is inside of the blocks package. So I think I've already told a little bit to most of the things. We have the interfaces that we can use to integrate the networks, and we have the extrapolation warning to detect some extrapolation. We then have the data generation that works with Latin hypercube sampling, and we can then use it to generate out of Modelica models some training data that we then can use to train ourselves on models. And we have the network generator that's a tool for defining and training of neural networks inside of Modelica. So it's using a Python backend to train them actually, but we can control it from Modelica, so you will see that later. And the model generator to automatically create us some Modelica models to use if we have an already trained network. So with that, we come to the learning objectives of this tutorial. Obviously, it's for you to get to know the library itself and the concepts behind it, as well as how to use the main functions. And we are creating an example of how to create and implement a surrogate model in Modelica. So this is our use case. We use the modified Clara vapor cycle. So this is an example that you already have in your tutorial package, and it's a basic refrigerant cycle with CO2. We have there two controllers. One is controlling the high pressure in front of the condenser, and the other controller controls the compressor, and it's based on the outlet temperature at our chiller. So it's relatively simple refrigeration cycle. And we have, or what we want to do is, we want to create what we see at the bottom here, in the bottom half to the left. That is a surrogate model of the condenser component that's also marked up there. So this is what we are going to do today. And I think before we start with creating our models, it's always important for neural networks what kind of training data we have, and before you can create or train a neural network, you always have to ask yourself what inputs you want, what outputs you want, how you capture all of your physical influences, how you can effectively bring back your model or your outputs in your model so that you have all important information. And also the data should reflect all important system behaviors. And in our use case example, we have three different inputs. We have the refrigerant pressure, the enthalpy of the refrigerant, as well as the mass flow. And we want to predict, in our case, the heat flow as well as the pressure drops on both sides, so on the air side also. And the air side is, in our case, it's constant, so because of that, we don't have to use them as additional inputs. Make our model a little bit more simple. So this is the outline for this training or this tutorial. We first start with the data generation, where we're creating a model to get us some training data. We then, in the second step, are going to train ourselves some neural network and already test it in an open loop tester, and then create our slow rate model and bring back the model into the whole cycle. And then we, in the last point, we can compare it with the physical model and also do some tests on the extrapolation as well. Yeah, with that, I think we start with the first practical work for you. Or before, I think I give some information how to use the data generator. I think you can, if you've not done it yet, you can open your Daimler and run the start script we have provided you, so that you have the library, SMArtInt class library, the Clara library, as well as the tutorial package open. And we start with the data generation. So obviously we're using our data generator. And I've mentioned before, it uses a Latin hypercube sampling as a method to generate some inputs. And we have three different types of data generators. So the first one is a stationary LIS that we use to generate steady state data. This is what we are using today. We can use that to get ourselves some data for feed-forward neural networks. Then we also have for dynamic components a dynamic Latent hypercube sampling block. This one is time-based, and then we'll store ourselves some data every 10 seconds or whatever we want to, or whatever time we define here. And the last one is more a block of to compare results. It's also time-based, but we don't store there some data, so it's just a Latent hypercube sampling that provides us with some random test data. And what the data generator does, it's creating us an output of CSV files, an input and output file, and we have there our selected variables as well as the values we are selecting in our model. But we will see that in a second. If you don't know what Latent hypercube sampling, I've used this word before, it's a method to sample some data in a specific way. And the concept is that we have that we have our parameter ranges, and we are divided it into our sample numbers, and then we can equally put there some points in it, so that we have in each row and each column 1 point or one data point. And if we compare to the Monte Carlo sampling on the left side, that's more random. Then we see that there's better coverage, and there are no empty spaces and no parts where multiple points are. So it's a good way to create sampling without clustering and gaps. And it's more uniform coverage. Yeah, so this brings us to our block that we're using in the model we are creating. It's a stationary LIS, and it's we're using this method to create us some inputs. And the block is created that way that it provides the Latent hypercube sampling inputs or the values, and it keeps them steady state until our outputs that we define from our cycle are also steady state. I think you will also see that when we do it. And if they are steady state, then we have an update of our inputs, so then we get new values, and our model can also create a new output that's then going to be tracked off the block, and it's then updating the values again. So there's a cycle, and this runs through until all assemblies are simulated. And yeah, there's also some methods to handle or make it more robust against solver issues or problems. So if there are too many rejected steps in the simulation, then the values or the specific input values are skipped, and the next one is used. And yeah, so as it says in the bottom, it's automatically stopping once our samples are processed. So you don't have to worry about that. And this brings us to our first task. On the right side, we see this is what we're creating now. And we have here our condenser model. This is the physical model. In the next slides, there is some explanation how to create this model. And yeah, we are varying our values, our input values for our new network. So the outlet pressure, as well as the inlet density and the mass flow. And we are tracking our outputs of the neural network. So this is then the heat transfer or the Q flow, as well as the pressure drops. And as I said earlier, we are assuming a constant air side, so we don't have to put there some additional inputs or varying some additional values. Yeah, so this log is then storing and updating the values once the state is achieved. We need to define some boundaries. I've chosen here some boundaries that we are using, and they are also in the explanation on the next slides. And in our case, we are using 4,000 different samples, or we want to create 4,000 samples. So yeah, I think with that, the practical part starts. Yeah, you can open or run the start script to open all of the packages. So maybe, I don't know if you, it might be helpful if you have the PowerPoint slides also open so that you can copy some values. But I will maybe show you. So if you have your Daimler open, all the models that we are building are also present in our tutorial package. So if we see here the data generation model, it's exactly that what we want to build. And this is what we want to build, and this is what we want to create. So for you, that means we are, or you probably should create a new package in the first step that you can call a tutorial or whatever you want. And then you're generate or creating a new model that's called data generation. And then maybe I will show how to use or how to read the instructions on the next slides. Maybe I will give you a short time that you can all create your packages and models. Yeah, so basically the instructions here are that you always have the step number at the top, and you see then your diagonal screen or how it should look after you finish the step. So you have here also the text. And in this first step, we have to add the Clara Sim Center as well as the condenser component. We can easily copy that. So if yeah, maybe I'll show it later. But yeah, so this is what we have to do for the Clara Sim Center. This is how this works. Then we have all the components that are added in one step. We see there's the name of the component and the path to the component. So the Sim Center is just in the Clara package at the top level. You can find it. And then we see also which parameter we have to adjust. In this case, we just have to select there the CO2 medium. And yeah, maybe I will just show this really quick. So you should all have created a new model. I just take this one. And what we can do then is that when you are in the SMArtInt Plus tutorial, you can open the physical cycle that we have. So this is our base model that we want to, where we want to create a surrogate from. And we can then select our condenser, copy it, and just paste it here, just like this. And this has the advantage that if we look at the parameters, we don't have to define here anything, and everything is already defined from our physical cycle. And what we then have to do is we can go to the Clara, where the PowerPoint says where the path is. We have here the Sim Center. We can just drag it in, double click on it, have to move to media materials. And I believe fluid 1, yeah, fluid 1 is the one we have to change. And we can then select here our CO2 medium, just like that. And this is the first step. And yeah, I think that there are some following steps in the PowerPoint. I'm going to switch back. So it's quite useful for you to have them open separately. On one screen, it's always a little bit of trouble, but yeah, if you don't want to fill out the parameters, you can also just copy the components from the data generation model that exists. Or if you don't want to create it at all, you could just use the data generation model we've provided you with. That's up to you. Yeah. I think there are different steps here. I have to add first some flow gas or some flow sources. And it's a little bit step by step. I don't know. I should show it step by step, or if you want to have it there at the end, you should see the results similar to this.
Maybe you could comment on the color of the interfaces, because the components look very similar, but they have different meanings.
So yeah, we have, like Stefan said, there are different colors. So in the Clara library, for those of you who never worked with it or used it, there are different ports. We see at the top there are some gray connectors. Those are gas connectors for air side. And at the bottom are blue connectors. This is VLE interfaces. So VLE is vapor liquid equilibrium. And this is what our CO2 model is defined as. So it's obviously a gas, but it's in this case it's defined as VLE, and yeah. Yeah, I will probably give you some time to build the model or copy the model.
Yeah, questions you can also ask, no? So
yeah, then if we any time to interrupt to ask, you also can ask Johannes. And you don't have to worry if something's not running or you're not getting the right results due to any reason. In this package, there are also the results of every step, so you don't miss out on the next step if you have the first step not complete or something. So then you can just use what we provided you with, and you can continue then.
I delete if I can as in this
yeah, maybe one explanation about the ordering of the interface. So the RFS is currently concept how the interfaces are vectorized and what values are addressed and stored.
Yeah, maybe I was showed in
Was is that not strict books?
So when you're creating this model, and then you have to provide here some values, and there are these output arrays and input arrays. Inside of this block, you can define how many variables you want to use. In our case, these are our inputs: the pressure, the enthalpy, and the mass flow. That is the result of this Latin hypercube sampling that's then be varied, and as well as the number of values you want to track. These are then our outputs of our neural network: the Q flow, the pressure drops, and yeah, it's always the way that the first output of the array is also the first variable you're defining here. So you have to define here some array. So the first minimal boundary value you define is also for the first output or the first value of the array, as well as here for the variable names. So the first one is here the pressure out, and yeah, then the second one is the enthalpy, and the third one is the mass flow. So this is always the way. So what you're defining here is, or the order you define here is the order that it's in the array. And that's the same for the values you're putting in or you're tracking. And it's not that much important which order you have. It's always important that your names are fitting to how you connect it. So if you're connecting the real expression with the Q-flow as the first array input, then you also have to define it here as in the names as the first entry.
This is something which is not automatic.
No.
You have to do it really with care and need to consider that when connecting the interfaces.
Yeah.
The correct define order of the variable. Otherwise, you get a mess problem.
Yeah. Yeah, in principle, you don't have to define these names, but it's quite useful because these names then also appear in your output tables, also then in the neural network training, they are also in there so that you can see directly, okay, which parameter I'm training and how good is it. And there it's then quite useful if you have there some names and not just numbers or so.
I can use every name of the variable I want to.
Of course, yeah. It's just for you that you can then later what you have trained and what are your inputs and outputs. So this is
Start values are most important.
that is
You have the boundaries you.
you have in principle here here's some if you look inside of this plot, you have here some first order, so you could probably put here some start values if you need to, if it's not starting the simulation, but it should be due to your boundaries, it should be simulated, but hopefully. But if it's not the case, you have the option to, but by defining there some values. So I think we should, or it's time to continue. Maybe I will just, maybe you already did this, I'm not sure, or also the next step. This first step is just to show how this block works and what you can do if there's some errors or something like this and your simulation not runs through. Then you can, if you see here, then we can use the backup file to continue the simulation from the last sample that was correct or the last one that was simulated. And maybe I will just show this Modelica. So we have here our model. In this first example, we are choosing here not the big simulation time that we need to run all 4,000 samples, but we will choose smaller one. And when we simulate this model, we should see, hopefully it's working. So the simulation starts and 1,000 seconds are quite fast. we already see that there's opening a window in our Explorer. These are our results. I will just put it a little bit smaller. So we have here our input and our output files. And we have here this data checkpoint of SMArtInt. And we could also take a look in here. Here we now see our variable names that we defined inside of our block. So this is where you can find them the first time after defining them. And we see here now all the values that are our LIS block had as an output, and yeah, the different variations of the values. And we see right now here for me it's simulated 76 different samples, but not the 4,000 I wanted to, because I selected too low simulation time. What we can do then, and what is the next step in the tutorial for you as well, was to select the bigger time, like 1E7, and also we can then say inside of our stationary LIS block that we want to continue our simulation, because we had already simulated, in this case, just 75 or 76 samples. And we can then go here inside of our working directory. There you can always find your data. There's this training data folder, and with a timestamp, then our here our checkpoint file. We can then select this like that, and we are able to rerun this for this large time. I can maybe start this here also. And one problem we have is when we have this large simulation time, we are not getting any info on how long our model is running, because we're looking here at the CPU time or the simulation time. We don't know which or how many samples we already simulated. And because of that, we have implemented a variable inside of our block. So if we're going here to our stationary LIS block, we have here this progress variable. We can select this, and inside of here we have now an overview of how many samples we already simulated. So this is the percent. So now we are like having 14% of our 4,000 samples. And we can track this way how far or fast or how long our simulation is probably going to take. Due to the steady state concept, not every sample is taking the same time, but most of them are also depending on the model that we are, on the physical model that we are having there, but most of them are quite similar in simulation time. So that way we can just track how our progress is. And once this is run through, we should also see the folder opening and have there the complete 4,000 samples. Switch back to presentation. So this is probably what we have here at this slide. The simulation or this continuous simulation of the backup file, and then we can simulate all the 4,000 samples with the large simulation time. Like I showed, we have this progress variable to see how far we are. And what this checkpoint also does is it's removing the last sample or the sample that if our simulation gets stuck or not run through then this last value is going to be removed, so that we don't have there an issue if we're starting from backup file. We don't have the same value again, and it has the same problem due to maybe some combination of inputs that are not valid for our physical model. Yeah.
This is more like we have a path thing, or what is the choose recipe? Because you mentioned the slides before, there's also some skill values that might be problematic that you.
Yeah, so this is more for if there's some hard error that your that the simulation stops and not run through. The other one is in the background. You can also define inside of this block how many rejected steps are allowed. If you put this to a small number, then you will see that there's also possibility that not 4,000 samples are there, even if it's running through, but then there are some values or some combinations that are omitted. So yeah. Yeah, so if you did this and or as I showed you, you then have in your working directory in this training data path folder and the timestamp folder, you have then your results. And these results we can directly use in our network generator to for our training process. So this is quite useful. And this is then also our next part of this tutorial, the training of the neural network. And if you don't, or if your data generation wasn't successful or whatever, or you not, or it's still running, then you could also use in the next part the data that are in our in the tutorial resources. Or if you're joining after downloading the library. Yeah, but first I will give a real short, quick introduction into neural networks, or in this case, before neural networks. This is what we are training in this example, and it's the simplest form of neural networks. And we just have, like, this is the simplest possible structure, probably. You have just your input, then you have this hidden layer. These two dots are our neurons of our neural network, and we have an output neuron. And when we see here, this is the principle behind it. So it's in theory, it's just a mathematical equation down here. So we have our input x, and it's then be calculated. So every neuron has a bias value, and there are then weights connecting each layer and we can have multiple layers, and we can also have multiple neurons. In this example, it's just one layer and two neurons. And we also have like some activation functions. This can be just simply linear activation, where we don't have one, we just have multiplied by one, as well as the nonlinear activation function. I can show, I think, in the next slide. There are the most popular ones. And so what we can see, or what we can take from this slide, is probably that the more complex, or the more neurons, the more layers a neural network has, the more connections are there. So more weights connecting the neurons, and more biases, obviously. And that way we can have here like more complex equation that is then going to be trained, or that is going to be adjusted to our problem. If we have, or if you have more complex application, you also need more complex neural networks. So here are some of the most popular activation functions. I think everyone who already had some contact to machine learning knows most of them, but for those of you who never seen or worked in machine learning. Yeah, I think the most popular one is probably the ReLU function that's used a lot. Yeah. This brings us to our network generator. In the first part, we had the data generator, and now we have the network generator. This is also the reason why the download took so long, because in this network generator is based on a Python backend that's compiled. So this is in the library sources, and this makes the library a little bit heavy in the size. And yeah, what we can do is use it to train from data. And yeah, we have also inside of this network generator, there's a feature of SMArtInt that allows us to train dimensionless neural networks. We're not using this right now, but it's possible. And if you're interested in this, there's also an example in the library where you can take a look at. I think if you simulate it, there should also be some automatic results in Daimler, where then difference between dimensionless and normal neural networks are visible. Maybe we can also take a look at this at the end of this tutorial if there's some interest. Yeah, but for now, we want to use the network generator. What we need, or what the network generator needs, is input, is training data. We already created this the step before. And what we get from our network generator is a trained TensorFlow model, as well as a TensorFlow Lite model. The TensorFlow Lite model is what we, in the end, are bringing back to Modelica. The TensorFlow model is if you want to adjust something in Python or whatever, you can use this. This is just an outcome of our training process because we're using TensorFlow and then exporting into TensorFlow Lite. And we also get some visualization of our training metrics, how good our training process was or is. And yeah, we will see that later. So this is on the right side how our network generator looks in Modelica. We have always this on the left, this block. This is the sim center of the network generator. Inside of this, we define our hyperparameters for the training. So yeah, everything that's important, how many training epochs we want to have, what optimizer we want to use, what kind of loss function we want to apply, and stuff like this. So there's also some explanation in the documentation. I will show you in quick or this slide probably in Daimler how it looks. And right now we are supporting 13 different layer types. As you see on the right side, you can always connect them just like this. You have at the top the input, at the bottom the output, and in between you can drag and drop your different layer blocks, and you can, by double clicking and adjusting parameters, you can then define the number of neurons, also called units. And you can define which activation function the block should have, and there are different kinds that you can use. And yeah, as it says, you can use training data like we did now that we are creating, or some synthetic data that you are creating from some models with the data generator, or you can use if you have some measurement data that's working as well. So it's not depending on the process we did before. It's just for us to have some data that we can work with. Yeah, this is then what this network generator also had is this visualization during the simulation or during the training. for us to see how good or how bad our training is. And the log process of the training, where we can see which epoch we are and which learn rate we have, and all that is also stored in the Modelica log. We can see it live in the Damson Excel, but I will show this also, I think, in the process. The network generator also has some additional features like early stopping. This is a method used for neural networks to make sure that you're not overfitting your data set, and this is most or often the case if your neural network is too complex for the data and then you are learning points and not the behavior or the equations behind, if there are some. And so for early stopping, or this is what the model or the network generator does, is it splits your training data in some training and validation data, and it then tracks how the improvement is. And if your validation data is not improving, but the training data is, because you're learning on your training data, then it automatically stops and you get the best results you have to this point. So this is quite useful. And the other thing we have implemented is learning rate scheduling. So the learning rate defines how fast your optimizer are adjusting the gradients of these learnable parameters from the network. And normally you start with a higher rate at the beginning to have a faster convergence, and later, if you want it to be stable and you want to do some fine tuning, then it should be lower. And you can do this by this learning rate scheduler, where you define then some starting learn rate, and you can also define after how many epochs without your results getting better, you can then it drops, and you can define how much it drops and how fast it drops. So right here we see our training loss and also the validation loss, and we see in purple that is the learn rate. So we start with 10 E minus 3, and then drops down to 10 E minus 7 at the end. And this is also quite useful. And these features are accessible about with the simulation center or the sim center. For you, the task would be in the first step to create a new model and add a sim center as well as input and output. You can then define these following parameters, and in the sim center you can do it the same. You can do it simultaneously, and what we can then do is simulate it for 1 second. And what we then probably will see is a bad training result, because our model is just consisting of 1 input and 1 output, and there's nothing really to train or to learn. I think there are then 3 neurons or something like this, and this is not capable of showing or capable of representing our data set that we have, or physical model. And maybe I switch really quick. So this is what the result of our Latin hypercube sampling looks like. If we look at the progress now, there is 100%, exactly what we wanted to have. And if I look here, we should have here now a new folder. And if we now look at our input data and can scroll down here a little bit, then we should see that we have here 4,000 values. Not exactly, because the first value is the name. It's the one value that's missing is the one that we have cancelled due to our backup or simulation from backup file. Yeah, and this training data we can use, but you could also, if you're having this in this tutorial folder, you can also use the training data we have here in the SMArtInt Plus tutorial resources. There's also a training data. This is the same. It's probably something I didn't mention earlier, but inside of this block, you can define the number of samples, obviously, but you can also define here some seed. If you have 0, then it's always random, and there are always different values. In our case, we have here 42, so that we all have the common ground and all have the same training data. And this is also the training data that we have provided you within the folder of the training resources. Yeah, and what we can then do is, or if we follow now the instructions of the, this is probably something I could also show. If we now take a look at our SMArtInt Plus library, and inside of this blocks, we now want to use the network generator. And if we double click on this package, we also see that the documentation is opening. And here's some base instructions how to use this library, and this is as well for the data generator. So always you have like inside of this information you have some basic instructions and getting started, how to where you can find informations as well. And then you have inside of these components you have always an explanation what this feature does and how to use it. For the network generator, also for you, maybe what's interesting is in this layers. Here you see all the layers that are supported right now or that we have implemented right now. And here also some short explanations what this layer or a specific layer type does and how it can be used, and as well as some common layer parameters that most of the layers have, like the units, the number of neurons, and the activation function is also quite popular and are in most of these layers. So I think with this we can start with the task. Maybe you already did. I think we should continue. We left or started the break thing right here, front of the training of the neural network, and this is a practical task for you. I will also do it here so that we can see it. I've just added the sim center here in my model. Put there, I think, the values of the slides, the epochs and everything, and down here I've selected my input data, my training data, as well as the output data. I've used in this the data we provided you with, and not this specific one I've created, but it's the same data, so it doesn't matter. And what we can do here also is this live visualization. We can select here if we want to see live results or not. I think it's always a good idea to see them. And you can define here the frequency of epochs on how often it should update the plot. This is a little bit, if you could do one, then it would be after every epoch you would see a difference, but it's slowing down a little bit, or you are then creating some overhead. So probably, or most of the time, a number like 10 or 20 is a good number. to track the results. But you will see that in a second when we create our model and simulate them. So now we have set up our sim center. And what we can do then is, if we go to our network generator and instead of this layers package, we can then put inside here an input and an output block. These blocks don't need any additional parameters or so. They're just for the network generator to know where it starts and where it ends. And the parameterization is gonna be from or is provided due to the training data we selected. And in Simula, it's enough to simulate for 1 second. I think in OpenModelica, if one of you, I don't know, is using OpenModelica right now, then it needs to be simulated for 2 seconds. And we can start it now and see what happens. As I said earlier, it should not have great results due to the fact that we have no real model or no real neural network to train. So first we can take a look at this Dynamo X. We see here some informations where our model informations and our model settings are saved to. So there's inside of our working directory, there's the SMArtInt worker model folder. This is not important for you at all, but and then we see also that here our plot opens. You take a look there. We have now here, maybe show the mouse, our different 3 different outputs we defined in our LIS block. The name should be the same. So if you change there any name, then it's this already was our training process due to early stopping, I think. We have a simple model, so there's no real nothing to learn or so, and the progress isn't good in between, so it stops quite fast after. If we now look at our training history, that's and this folder that opens up, then we see after 35, 36 epochs it's stopped, and we see the loss is quite high, so there was no good training. We also have here these plots for the individual values. This is the prediction and the reference. For this specific case, we have to, or I have to say, the pressure drop on the air side is a constant value based on this, I think, 3.46. So because of that, it's just here, it should be 1 point also, and we see we have a wide range in the prediction, so it's not a good prediction at all. And we see here also for some test values that it's not good. And in general, normally you have this a plot like this where you have the prediction and the reference, and in the ideal case, all the points would be on this diagonal line. And so we see we can't, with our network how it is right now, we can't get good results. And also for the Q flow, it's not looking better at all. So we have to change something, and this is what we are going to do in the next step. So if I switch back, I don't know, maybe you simulated this also, then you should see equal results. And what we can do to get better results is to improve, in our case, the model complexity. We can also add an input and output scaler. This is also something that's quite helpful by training neural networks, is to scale the data so that the actual layers are in a range of 0 to 1. so that we don't have like big biases and weights, and the gradings are also a little bit lower. This is quite helpful. We can improve the number of neurons per layer, as you have in mind maybe from earlier. The equation that results then is going to get more complex, and we can use nonlinear activations. And yeah, this is probably something you could try now to create a more complex model. You can also vary a little bit the hyperparameters. So the number of epochs, how long you want to train it, the learning rate maybe. Yeah, if you take it too or maybe too low, then you will see that there's also, it takes quite some time to get good results. Yeah, so you could just try it a little bit out. I think maybe it's useful for you if you want to create or get good results. Here's some best practice tips in the presentation. I think you can take a look at that. Or what you also can do is, if you want to have good results, you can also take a look at the training model that we provided you with, and you can maybe a little bit orientate on how many layers, how many neurons or settings we have there. But I will also show, for those of you who are not able to do it, I will just show how much of an impact some things have. So if we maybe just start by adding scalars, and this is quite simple to add a scalar. We can just drop it in. In the scalar, we have then to define if it's an input or an output scalar. In our case, it's the input scalar. We have here two scaling methods, min-max scalar or standard scalar. Yeah, I think in this case it's not that important which one you use, but there can be some difference maybe depending a little bit on the data you have. But scaling in general is helpful. We can then also put here an output scalar. We have then to change to output. It's already in max scalar. It's good for us. And then these dense layers are the base layers of neural networks. So this is what we've seen there. This is just this fully connected neurons. We can drop in some of these layers. We see here we have now 10 neurons in this first layer, linear activation, and also there's some regularization. This is more detailed. We don't need this right now. This is also for overfitting and stuff like this. This is all described in this documentation of the library. For this case, we maybe just try the nonlinear activation function, and maybe just put here 32, and we can see if we maybe try a second one, and maybe we can just run the simulation and see if it's already better or if it's worse or whatever. So we will see when it's running. In the training process, it's always a little bit of trying out. Experience helps that you don't have too big neural networks or too small. So you have always to consider a little bit what you want to or how complex your training data are, and depending on that, And now we see it's saying epoch 1, now epoch 10. So this was the first update we had. We see we have now already better results than before. We can also take a look at the dimension extent. We see here in which epoch we are, how our parameters are, what the loss is right now, how the learning rate is. And yeah, right now we have 200 EPOS, so we could also boost them up a little bit to get more better detail results. We see right now it's already looking quite good. Yeah, maybe we just let it run through. Maybe we can see if the early stopping is going to be activated or not. If it's not activated, then we have just 200 EPOS of training, and yeah, you can see. Hopefully, it's not taking too long. So we see right now there is not a big adjustment. There was quite some update, but these are more slow. It already gets slower, and we already see that our learning rate schedule works. So we have now a lower learning rate than before, or what we started with. And yeah, but this means that we are now a little bit more into this fine-tuning area, and this is also quite good. Yeah, and we can, yeah, this way we can track it. Like I said before, this is the pressure drop of the air side is a constant value. So I think we are quite good, 3.46. An additional, and there's this deviation a little bit, but it's 1 E minus 8, so it's quite low. And if it's running through, then we should be able to see the results in the folder, and the same should apply for you. You are also, you can always, if it's finished, I will show afterwards. Yeah. So we take a look now. We should see here with 2 adjustments of our learning rate. Every time it fluctuates a little bit, we could probably, but this is not a loss, this is the MAE, but also here in the loss is some fluctuation. We could probably let the learning rate change a little bit earlier, so that there's, yeah, after less EPOS, but this is quite also good training history. If you look at the other results, this is probably not the best one to look at. This constant value, we see the difference is not that big. For the pressure drop of the coolant, we have here yeah, we see in this plot we see the reference values or the test values we have and the prediction, and there most parts are looking quite good, quite matching. Yeah, at some points you see there's a little bit of edge of the blue, then it's a little bit shifted and not perfectly. But this was just our second try, so we can probably get better results. Also for the Q flow, you see some more shifted values. But we can get better results, but this was just by adding scalar and 2 dense layers, so there's a lot of potential. And also we see inside here we get this model configuration JSON data file. We will use that later. I can maybe just show it. Inside here there are all of the important settings and values, like the names, the dimensions, what kind of model we have, as well as the pass-through training data. We need this a little bit later for the automatic release iteration. And yeah, so yeah, you could try a little bit out and simulate here the different, or train different networks and see how good they are. One one thing I wanted to show is if we look here in our log file after training or in the demo, actually we have here the complete training process. So it starts with the model that we defined. So we see here our input scalar, our dense layer, 32 neurons we defined, the same for the next dense layer we defined, and the output scalar. And then, yeah, we have to bring it down to 3 values because we have 3 outputs, and then the output scalar can apply to that. So we see if we would change now here anything and re-simulate, then this would also be different. So yeah, this is what our network in the end looks. Also, we have here like the whole training process until the 200 epochs, and we get here the information where our file is saved. We can always turn on and off if it's open this result directory or if it's not opening it. Yeah. And you can, yeah, just if you have new data but you want to train the same model, you can just select here different files, just like that. It's easy. And or you can copy some structures if you say model already defined somewhere that was good for equal case or a similar case, then you can just copy it and reuse it or duplicate the model and exchange the path. So you're able to use all of the advantages that Daimler and Modelica offers there, and then yeah, simply train your network without needing it to touch or to write Python code or whatever code or whatever language you want to use to train it. And yeah, if we simulate, I don't know if we want to do it right now. I think it's take a little bit longer than the example model we have here. We see here we have also a scalar and some dense layer. We also have here a residual layer. This is yeah, a more specific layer. There's some description in the layers package. This is a layer for deeper neural networks. So if we add more layers, then it's the output of this block is what a dense layer would have, as well as the inputs. So this is a little bit like a bypass and a dense layer combined, so that you, if you go deeper in the network, then you have also the informations from the beginning. But I think in this case also it should be quite good by using just dense layers. We've seen that. Probably I can show the result we were getting if we would simulate it completely like this. I think here's this example. There's a high epoch, like 1000. We had 200 last time, and now it's a little bit more. I think the rest is quite similar what we had before. And if we now take a look at the results here, then we see now we have a little bit more steps. Our learning rate, pressure drop of the air side constant value is a little bit worse, I think. I don't know why exactly, but it's not that big of a deal. If you take a look at the other values, then there's good results. So if we take a look at the Q flow, maybe the last time we had some more points where the blue points or the reference points were not matched so good. But in this example, most of the points are neatly aligned. I think this one here at the top maybe is a little bit worse, but this is probably quite good training results. Yeah. So probably if you did some of the training or yeah, you try or you tried out a little bit, I think we can then proceed with the next step. I think it's also time to do this. If you don't have a good model, you can, as I shown before, use the one in this resources that we trained. So you find it in your tutorial folder, and yeah, you can then use this T-Flight model here for the next steps. Yeah. So the next step would be to bring these results back to Modenica. We have two approaches. One is an automatic way using our model generator. The other one is perfect. Is the interface block of the SMArtInt library. This offers us a little bit more flexibility because we can easily exchange the model by just defining another path or switching input-output dimensions. But the automatic one is, yeah, I think a little bit more if you just want to directly use your model inside Modenica. So this brings us to our open loop tester. For this open loop tester, we use the model generator. This is also an external C function, and that generates us a Modenica model, a mode file from the trained neural network. We can use their TensorFlow Lite or 1NX as input formats. And we get a Modenica model or a JSON config file. And the results are also saved in our working directory. Yeah, so this is what the task would look like for you. We would implement it in the open loop way so that we don't have any controller influence or feedback effects. If we would put it inside of the site directly, then we would have those. And yeah, we can use this to check how good our training process was. And yeah. For this, you have or use this model generator. I can probably show this. If you have the slides open, you can also follow the steps. In the first step, you have to go to your SMArtInt class library and go to the model generator. And there's this create model, and you have to duplicate it. You can use duplicate class. You can insert a new package if you have created one, and then it should look like this. Yeah, if it looks like this, you can then double click on this E and select here your model that you want to use in Modenica. In our case, this would be inside of this tutorial package, resources, AI model condenser, and then this model T-Flight. You could change here between T-Flight and 1NX. Yeah, if you want to open an 1NX model, but we have a T-Flight model, so we choose this. And just like this. And then we have here different options. We could say or define if we want to use automatically generated names or if we want to define them. If we want to define them, we can define them in the Dimestem exit, and there's it's going to be asking you to type in some names. And we can also define if we want to have a simple interface, just meaning that we have an input and an output array. If we don't want this, then we get for every input and output a connector. In our case, we have 3 inputs, 3 outputs. It's okay, but I think if you having a neural network with maybe 30 or 40 inputs, outputs, then you don't want to have 40 connectors on each side. So you then are going to choose probably the input-output array structure. And what we can do, if we've trained our network with the network generator, we can also select here from config. And there we can then select our config file. That's also in this AI model folder that's created. And if we do that, we don't need to specify any names because these names are were already specified in the training processes or our training data. And we can do this. And if we have done this, then we can just simulate it. And by simulating it, after simulating it, I should open up this folder. We see here now we have an AI model, MO, and we have here already copied our flight model and copied our model config, so that we always know what kind of model this is. And then we can just drag it inside here, and we have a model that we can use. So inside of this AI model, it's also using the AI interface. It's just to have it easier for the user. I think if you all done this, then you can continue with the steps on the slides. It's creating a new model, or probably extending the physical cycle. And what we also do is that we remove the input ramp we had there and replace it by a more complex input for our chiller temperature, so that we have there a little bit more fluctuation and to see a little bit more than just 2 steady state points. I think this is here. Yes, this table, maybe I will do it right now. And we then had to get these real expressions here for our neural network inputs. What values we have there is the pressure. We have to here take into account that we have trained it in bars and not in Pascal. And I think the unit there is Pascal, so we have to divide it by 1.5. And we have the inlet enthalpy and of the condenser. And to get the inlet enthalpy, we can use this compressor outlets H outflow. So the outflow enthalpy of the component in front of the condenser is the inlet enthalpy of our condenser. And we can use the mass flow that's inside of this condenser component. And then we can just connect it. We'll show you that the model should have the right names, so it will be easy to connect these equations. And you have to drop in the model that you created in the step before. And after that, you will have an open loop tester that we can simulate, and where we could watch and compare the AI model Qflow and with the Qflow of our physical condenser that's inside of the cycling. And we could also, if we have activated it, we could also check for extrapolation. Yeah, maybe also for you to do it. We can, to shorten this thing up a little bit, we can copy the table and stuff. So if we have our new model here, and we would start by extending our physical cycle. Don't want to insert it there, just somewhere. Just like this. So we have here our model, and what we can do now, if we open up this already existing example to ease it a little bit fast, we can just copy these input values, maybe just here, and we can remove this. We can deselect it, this input. And what we can then do is copy this timetable like this, connect it, and we see inside here we have now some rising temperatures. This is in Kelvin, so yeah. And now what we want to, or what the main learning of this task is that we can then drop in our AI model, also do it a little bit bigger maybe. And if we hover now over the inputs we see here, this is our P out input as our pressure P outlet. We can just connect it. The same is here for H in. Our inlet enthalpy, can connect this also, and then we have the mass flow. We can just do it like this. And if we double click this, we can then, already we see here our inputs, our outputs that are defined in the comment. And we could say here we want to have an extrapolation warning activated. And, if we now simulate this, we should be able to compare the results. So run through successfully, hopefully. No, it failed. It's not good. File does not exist, okay. There seems some issue with our training data file. Because I'm not sure which config I used there. If you use the config that was generated with your model, then it should be right. Maybe I will just do this here by removing this. And if we change here to the model that we trained, then it should be okay. Yes, no. In our work directory, trained models. The last one was the one with the better results. We can open this up, and we can choose here our model config as well. I think this is because I moved the files to put them in these folders. Then I didn't update the config file. inside of the resources. Yeah, so now we are having a new, what is it? A new AI model. Probably should unload the old one, get some error duplicated names. And if I load this, then it should now be the new model, should look the same here. And now it should probably run. There should be the correct passes. Compiling. Now it should, now it runs. So yeah, you have to be a little bit aware of the data path. So if you're changing the where the training data lies, then it can be problematic. For this extrapolation, it needs the input training data to see if you're inside of this range or outside. So this is quite important there. And what you can do now is to compare the results. So, selecting here our Qflow of our AI model, it looks like this. And we could also go inside of the condenser. I think it's in summary. Yeah, summary, outline, Qflow. And then we see here it's quite good. In the open loop tester, we see at the end there's some difference between both of them. But if we now plot in a second window our extrapolation, then we see that the extrapolation of this neural network is false at the most of the time. But at the end, we see here that there's an extrapolation happening. And due to this extrapolation, we can see that there's some, or this is probably the reason for this this difference at the end that we see there. And yeah, so these neural networks are good at interpolating, but if you are extrapolating out of the training data range, then some things, or sometimes it can be that these predictions aren't so good or are worse. And you will see that this also later again. But this is the simple way to test your model in Daimler, and we've now used our first neural network inside of Daimler or Delica. And the next step would then be we switch back to our slides. The next step would then be to create a surrogate model. And I think this is also a task that you can do. For this surrogate model, we use directly the interface blocks of SMArtInt Plus. As we've seen before, there's already this extrapolation warning inside of it. These interfaces have also scalars included. We don't need them right now because we have already scalars inside of our new network. But sometimes you are scaling your data manually, or if you have a network where it is done outside of the training, then you can apply here some scalar. And we also have input and output smoothing. This is quite important for sometimes numerical reasons to break some nonlinear sequence and stuff like this. And all of these functions can be used or not. We've seen this with the extrapolation warning. We can activate it or deactivate it, depending on if we want to have better performance or if we want to check if it's good from the prediction. For surrogate models in general, I think we have here some basic information of hybrid models. There are different types that we can, or that you can build with SMArtInt or Delica. You can either have a complete physical model. You can exchange this complete physical model with an AI model, or you can exchange submodels of it. But you could also just create replaceable models like correlations, heat transfer functions, pressure drops that you can then train as AI model and have it exchangeable. We did something like this in the Disprovi project, research project, with measurement data of a power plant. And yeah, for this you can use also SMArtInt. And you could also have it just for some parameters you want to adjust, some correction factors or something like this. When you have measurement data, it should also be quite useful. And it's always depending on what kind of application you have and what you want to achieve there. But one thing that's always helpful, or you should always consider, is to have physical constraints inside of your model, surrogate model, so that there's always the mass balance, the energy balance correct. This is helpful, so that you don't, for example, in our case, we just predict the Q flow and not just predicting the output temperatures of both ports or something like this, because then the predictions vary between both values. You can have something that's not physical at all. Yeah. So then this would be the next task, the surrogate model for the physical condenser. It should look then like the one on the right side, and left side of the icon. We have here, like I told before, the consideration of mass and energy balance. What also could be important is that we have here, we want to have identical connectors so that we can just exchange this component by using the change class feature. And yeah, and inside of this we have a replaceable neural network. We can just by changing the path of the network, we can exchange our neural network behind the surrogate model. So it's not you have to create one time this surrogate model, and you can then, if you train a better neural network, you can just exchange the path to the network, and you can still use your surrogate model. Yeah, so you don't have to always create a new surrogate. Yeah, I think there's already a basic surrogate model that I've prepared, so it makes it a little bit easier, this task for all of us. We don't have to build this up. If you're interested, you can always look inside of the code and see how exactly it's done. I'll show there's some details also. The first step would be to duplicate or extend this model or the space model, and then we want to add our SMArtInt interface block, and we then have to define our values, like the number of inputs, number of outputs, where our model is, or pass to our model. And if we want to use extrapolation, we also have to define the path to the training data file. And what's quite important for the model to run in this closed loop cycle, we want to use it in the physical model in this closed loop. We then need the outlet, this power out, and we need there some first order block, and we have to also switch the init option, and have to provide some start values for the outlet. Yeah, I think maybe I will do it in parallel. Yeah, but maybe this is also good. This is the way the model is, or the surrogate model is created. This is what I talked about earlier, this energy balance and the mass balance. We see the energy balance, we have this Q flow. This Q flow is the prediction of our neural network, and Yeah, we have there on one side it's added, and on the other side it's going to taking form, and so this is a way we can ensure that our model is physical. Yeah. So maybe we'll just do it pretty quick together to show. And then we would now start in our SMArtInt Plus tutorial. We have here the surrogate model subpackage, and inside of this we have a complete surrogate model that you could also use, but we want to now create a new one. So we would use our base here, just extend it, and this was wrong. You can there select your package that you created. If you have one, we can just name it surrogate model, for example. And yeah, now we have to add our SMArtInt Plus interface. We find this in the SMArtInt Plus library, blocks interfaces. Here we have to define the type of neural network we have. If we use the automatic model generator, then it's going to be detected automatically. But here we have to define what kind of network we have. We just have a neural network feed forward. So we just take the neural network interface. We don't have some kind of recurrent neural network that requires a time series or that are working with time series for dynamic components. And inside here, now we have to define our path. We can then just go in this resources, AI model condenser, select our TIFF light model or the model you trained. We have 3 inputs, 3 outputs. We can here also, sometimes it's useful if we want to use analytic Jacobian. We can select here, we have here different options without analytical Jacobian support and with support. I believe, yeah, we have here some numerical way to calculate the deviation or the derivative of this neural network by different methods. We can choose here whatever method we want. And we also have the opportunity to do it by defining another neural network that has learned the derivative function of the first network. For TensorFlow light models or TensorFlow models, we have there also in the SMArtInt Plus library resources folder, there is a Python script that can create you such analytical neural network. So some libraries or some models are working faster with that. And in our case, we don't need this right now. Yeah, but this could be some useful sometimes. Yeah, right now we can select the path to training data file. This is because we don't have activated it. If we want any of these 3 methods, so there are different methods for the extrapolation, then we can select it here. The same procedure, just go where our training data is located. We have to switch here. And we need our input data, so we select it. And we say OK. And now we just have to connect it with these ports and have to yeah, it's easy if you have the same, or you follow the tutorial, then you should have the same order. And we can connect here the outputs also. Second one, third one. I think you can do it more beautiful than me, but it should work. And we also see here in our blog that we have here some Boolean output. This is the extrapolation output. So this turns true if the model is extrapolating. So if you want to do so, you can use it in your simulation and maybe switch to a physical model or whatever, or some default values if you say I don't trust the network when it's extrapolating, or stop the simulation or whatever. So this has some opportunities for you if you want to use it. And yeah, this surrogate model, if we have it like this, we can then use it. And to use it, we would duplicate our physical cycle. Duplicate class, and we can name it just _AI or so. And also put it in our created package. And inside of this model, we can then just by selecting the component, right-clicking on it, and then choosing this change class. And then we can go down here to our surrogate model, say OK. Then it will say it will remove all of these parameters. Probably most of them are some geometric things that we don't need because all of them is inside of our neural network. We can then say change and remove. And due to the fact that we have the same ports, it's already connected, and we don't have to consider anything else. And this should also be able to run if we simulate. No, probably not, because I forgot something. Yeah. As I said earlier, we have to define here these input-output filters. So we need here at the outlet this first order block. So if we have here 0, then there's no first order block. If we have 0.1 or whatever value we want to select for our time constant, then we have there an output block. And we also need to provide some start values on these. Take a look at the slides. This 5, 3 point. So these values are also on the slides. Just some start values, so that it will work, and then we should be able to see it running through in simulation.
Start in that case for the output is then 0.
Can you repeat? For what?
For the output, because before you didn't put any.
Yeah, then it's, if you didn't put the any value, then we'll have 0. Yeah, that's not the best. It took there so long. This is, should be faster. I don't know why it took the thing so long now. Well, you can try by deactivating this extrapolation warning. It should be faster, but I think that's not the issue here. Maybe it was the issue. So this extrapolation can also be, taking some simulation time. So if you want to deploy it, then it's often useful to test it with the extrapolation warning, but then for performance reasons turn it off and you see that it's working good or so. And if we know, we can now also keep this result. We can also simulate the physical model and compare them. Also take a look at the Q flow there. Summary, outline, it already shows that. Now we have to add our AI model, condense the Q flow. We see those are matching quite good, but we have to take here into account that also the controlling is taking part there. So if we have here, we have this complete system so controlled that at the end we have here the chiller outlet 20 degrees. And if we don't reach this 20 degrees, then compressor is adjusted. So and this because of this we also have to check what the compressor is doing. So this is also in the slides explained. I think we now take a look at the compressor, the power of the compressor, then we should see that this is also equal, almost equal. So we see that the surrogate model is doing what it should be doing. Maybe I'll switch back to the slides. I think we've done this. This is also what we've done some moments ago. The simulation and the compare. Here also the compressor power is quite interesting for us. And with that, I think we can come to the last part. This is just the comparison and the testing. For this, we want to use the extrapolation warning. We've used it already. It's like real-time monitoring of the input data, and it gives us the warning in Predica. And we have already seen this also that we can get a lower forecast quality if extrapolation is happening. And we have 3 different test procedures. Also seen that the first one is based on a convex hull or convex shell method. The second one is an easy or simplified density calculation. This is also good for many inputs because these convex hull need to be calculated, and if you have many inputs, then it's going to take some time, or I think there's a limit of 8 or so, 8 dimensions or 8 inputs, which equals then to 8 dimensions. So you can't use them for quite big neural networks, but you can then use one of the other 2 options. So the simplified density approach or the kernel density estimation. I think all of these have some examples in the tester section. where also the methods are explained inside of the blogs. So yeah. And we always get, if you use them directly, and I think in the neural network, you can also see this, we get in the graphical, in the graphical window, we can get these exclamation mark if there's an extrapolation happening. So if we scroll to the simulation time, then it should pop out sometimes. And we get the plot and of the Boolean also. Maybe this is or this plan for me just to show for you. I think it would be too much effort to build this right now. This shows again how to use or we can use this time Latin hypercube sampling from data generator that we used at the beginning of the session, and we can use it to create us some test data that we apply to both the physical and the surrogate model. And we have there two different cases then. The first case is with inputs or boundaries of this time Latin hypercube sampling block that are within our training range. And we have in the second case or second scenario, we have values or boundaries that also include values that was or were outside of our inputs. Or outside of our training range, so that we should see there's some extrapolation. And maybe I will just do this really quick. You have also this model here in this surrogate models. There's this tester surrogate. It looks like this. We can here on the parameter we can select which case we want to simulate, and based on that, we have here. Sorry. Yeah, so we have this model, and inside here in the parameter, the cases, here is the boundary switching, depending on which case we have. And we have here our physical model and our consensus surrogate model. And here in the top corner, we have our extrapolation block from our extrapolation package. And if we run this now, right now this block is also a random seed, so if we would run it again, it would look different. See, we have here the physical model always have a little bit of we have to get to the steady state. This is not the case for the AI model. This is more straight. This is due to the dynamic of the physical component. And we can also plot here our extrapolation warning. Here's the extrapolation detection. You can just plot our output. We already had here, due to the fact that we have random sampled data generation, we have the same boundaries but random values. So here are three cases where an extrapolation happens, probably just some values that are close to what we've seen in training. So because of that, I think the prediction quality is quite good, even though there's some extrapolation. But if we now are going to change this case to the extrapolation case and then do resimulation, we should see that there's a little bit more of extrapolation happening, and we also see that now our values aren't that good fitting the physical and the AI model. And we see also here in our on our blog that there's this extrapolation mark, and so this is what we can detect with the extrapolation tool, and sometimes it's matching okay, and sometimes there are quite bad results. You see in the cases where it's not extrapolating, the results are good. So this is always kind of an indicator on our operational area, and that we should use these neural networks. Switch back to this slide. I think the key takeaways are already told them, and so it's always important to select the train data also, and depending on what kind of model you want to build and what you want to what cases you want to have there. So if you would define different boundary conditions, you can have a wide range of application problems. I think one thing it's worth to say is that the models that are trained with SMArtInt can also, SMArtInt plus network generator can also be used with the open source SMArtInt library. So it's just a TF-Lite file, and you can also use that. So if you use SMArtInt plus and don't have a license anymore, you can just use SMArtInt, and also still can use your trained models inside of your simulations. The only disadvantage is that you don't have the additional features of the advanced interfaces like this input-output smoothing, the extrapolation warnings, scalars, the support for analytical Jacobians. So this is then missing, but you still can reintegrate your models to the yes, I think this is something if you want to take a look at the slides, short overview, the functions that are in SMArtInt and SMArtInt Plus, so where there's exactly the difference. And I think with that we are also near the end of our tutorial. Quick hint maybe that tomorrow we have also a presentation of a status paper we wrote for the SMArtInt library. If you're interested, you can join. There's a little bit more the focus on also different examples, what you can do and how to integrate, and what examples you can, or how you can use neural networks instead of simulations.